Hello, this is the second of these videos for this worksheet, worksheet 1, unit 2, looking at the multiple choice. So we're going on to question 9. A constant force of magnitude F is applied to a mass M for a time interval delta t. The magnitude of the impulse given to the force of the mass equals. Now here we just want to call up here we see that our impulse is given by this force times change in time times the time, or force times change in velocity. Actually the impulse gives us it is from the change of momentum. So going back, we can look at the answer for this one. So we get obviously it's going to be number C. It's going to be C here, because this is the impulse. So there's a direct question based on your understanding of the word impulse, things that you've really got to know. 10. Two carts of different mass M and capital M, small m and capital R, are connected by a spring. They are pushed together such that the spring is compressed. After the carts are released, the car mass M moves with velocity v. The change of momentum of the mass M is. Now, the thing that's important here is that you're going to get conservation of momentum. Now, conservation of momentum means that your momentum before, your P before, is equal to your P after. So, if there was zero momentum, if there's zero there, then your momentum after, if you've got mv, then obviously it's going to be equal to minus another mv. If this is the momentum of cart M, then this must be the momentum of cart capital M. So it must be this one over here. We're looking at 10b. It must equal minus v, because we get conservation of momentum. Started off with having zero momentum. They were stationary, they were just compressed. Let go. You've got going in one direction. You've got the mv going in that direction. So you must have an equal mv going in that direction. Fine, so there we have that one. Let's go on to the next question. Here we have 3 questions on this page. A lamp of weight W is suspended by a wire fixed to the ceiling. With reference to Newton's third law of motion, the force that is equal and opposite to W is the. So we've got the different forces now. Newton's third law says to every force there is equal and opposite force. Now, this W is the weight. And what is that caused by? Well, that weight is caused by the force of attraction between the earth and the object and this lamp. So the equal and opposite force would be this one, the force exerted by the lamp on the earth. That's the equal and opposite force. So the earth is attracting the lamp downwards like that with its weight, and then this lamp would be attracting in the other direction on the earth, that W. So you've got to make sure that you get those pairs correctly. So it would be C. 12. A constant force acts on a mass that is initially at rest. Which of the following graphs best shows how the kinetic energy Ek of the mass changes with the work done on the mass? Alright, now the friction is negligible. That's an important point there that we're going to have to take into consideration. So we have here that the kinetic energy, we're looking at the kinetic energy and the work. Now, what we have to realize here is that work is measured in joules, and kinetic energy is also measured in, well, let me just write it like this, is measured also in joules. So the work, all that work that is done on that block is actually being put into kinetic energy, because there's no energy loss to friction to overcome. That force doesn't have to overcome any friction. So that force applied on that object causes it to accelerate, and that acceleration leads to an increase of the kinetic energy. So it would be A here, because there's a direct proportion here between the kinetic energy and the work, because all the work is actually put into the kinetic energy. That's where it goes into the kinetic energy. Just bring this up a little bit. Sorry, just going to move this page. Here we are. Two balls of different mass are dropped from the top of a tall building one after another. The distance between the balls increased with time, depends on the initial velocity only, remains constant, depends on the mass of the balls. So they are dropped from the top of a building one after another. So what we've got to realize here is that firstly the masses don't make any difference to that. We've got the situation here that the S is equal to 1/2 AT squared. So if we take the ball, let's just take a situation with this, and we'll take that there's a 1 second drop, and let's say we've got ball A and B. Alright, so after 1 second, and let's just say take A is equal to 5 meters per second to the minus 2. Sorry, not 5, but a half time. It would actually be 10, but a half times A. So after 1 second, we're going to have ball A would equal 0. It hasn't been dropped yet. And ball B, if it's been dropped, that will be 5 meters. Now after 2 seconds, ball A would equal 5, and ball B, the distance traveled, would equal, it's 2 squared times 5, so it's going to be 20 meters. And after 3 seconds, ball A would equal 20, and ball C would equal, now this is going to be 9 times 4 would actually equal 36 meters. So the difference between them would be 5, 15, 16. So we can see here that the distance between them is actually increasing. So it increases with time. So sometimes doing something like this is useful. Just trying out a simple situation, just trying it out and seeing what the results would be. Going into our next page, we've got 14. The graph shows how the velocity of a particle varies with time. So what's the velocity? It's negative here. It starts off being negative. It actually slows down, it deaccelerates or slows down in the negative direction. It starts to become 0 and then increases. Now the important thing to realize that the slope equals what for a velocity time graph? That's right, it's the acceleration. And because it's a straight line, the acceleration is always the same. So it's got to be C or D. We can see that this graph is a positive graph, so it must be C for this one. Okay, next page. Right, here we have an aircraft is flying at a constant speed in a horizontal circle. Which of the following diagrams best illustrates the force acting on the wings of the airplane? So we've got these different forces. Now, remember, when it's going in a horizontal circle, we've got something like that. If I draw a circle, well, I try to draw a circle. I'm not very good at drawing circles on this thing, but anyway, just imagine that's a circle. Now, it's going in a circle, and if that's the center of the circle, the force, the resultant force, is always inwards towards the center of the circle, the resultant force of all the forces acting upon them. Now, there are actually only two forces acting on this, and because it's staying in a horizontal circle, the vertical forces are actually in equilibrium. So if we look at this, we've got the force. This would be to W, its weight, and this would be the reaction force of the aeroplane with the air friction pushing the plane with a certain force. It's actually going to be D. If you have a look at this, the resultant of these two forces is inwards like that. That's a resultant force. You see? The resultant force. This, if I go back here, the vertical component of this directly cancels out the weight, leaving a force that goes in towards the center. The resultant force of this one is in that direction. This one over here, this is not giving this one over here is actually the resultant forces. These are not actually the forces acting, because this force obviously of the plane, the wings are always at right angles to the wings, so this is not correct. So it's actually going to be D. Looking at 16, we have, for a particle moving at a constant speed in a horizontal circle, the work done by the centripetal force is, it's going to be 0. Now, why do we say 0? Because work is equal to force times the distance times the cos of the angle between them. So if I say, let me use my same diagram, I'll just use a different color with it. We've got the circular, it's going like that, how it's going. This is the force. So it's always 90 degrees to the direction at any time. You see, it's 90 degrees. There's always this 90 degrees. And we know the cos of 90 is 0. So it's going to be 0. There's no actual work done, because there's no movement in the direction of the force. The movement is always at right angles to the force. Good, so I'm going to stop this portion at this time, and you will be able to get the rest of this worksheet in the next video. Thank you very much.